Welcome to lecture 16, gradient descent convergence analysis. Will now culminate in accelerated gradient descent. I'll be spending some part of today's class also doing demos. Um, so I'll probably put the link on Teams. And, the same link. Okay, so you all have access to it in case you want to run through it as well. So we were at this point on Thursday where we discussed Nestrauss and Pauliak's accelerated gradient descent. And as a homework, I had given some food for thought. What would be that gap bridging, right, through Nestrauss descent for the Lipschitz continuity case? Okay, so recall that we had the best case using smooth and strongly convex functions. And there we had log of 1 by epsilon, omega log of 1 by epsilon. Could like to go that way. And basically, we are saying for every 10% or every tenfold increase in the precision, right, you would require just 10 more iterations, which is very impressive. However, we also looked at lower bounds of convexity, and we said we'll not look at proofs as such. But what bothered us, based on existential functions, to which I gave you some external link, right? So what bothered us was in the case of smooth functions, we have a gap. The gap was that gradient descends at LR square by 2t, error, right? Error of at least LR square by 2t, whereas the lower bound using some existential functions said that it should be LR square by t square, t plus 1 square, basically, right? And this is what we've been trying to bridge. Can the two become closer? Okay. And toward that, well, I also said that for smooth and strongly convex functions, there seems to be slight difference, but it's not actually a difference, right? Because I pointed out last time they're the same order. Under root kappa minus 1 divided by under root kappa plus 1 raised to t minus 1. Now, one way is you can take the squared inside, but the kappa minus 1 or square root kappa minus 1, that's not a big concern for us. Those are different factors. Right? I think this t minus 1 in the exponent and t in the exponent, they are comparable. This 2 can always be factored in. Okay, with that, let's look at why we said we could try and bridge the gap in the previous case, right? The second last case, case 3 rather. Smooth functions. Why was smooth functions without strong convexity? Okay. Smooth functions and convexity, obviously. How we can bridge the gap. And that's where accelerated gradient descent becomes interesting. And we found a reason why gradient descent might be slow. I zoomed into this figure and showed that there's a lot of oscillation. And can we add some momentum from the progress made so far so that we tend to go slightly straighter instead of oscillating? And in that context, we had said the whole idea is we'll come up with a velocity. The velocity can then be complemented with gradient descent. Okay, this is what we had. So velocity complemented with gradient descent. Okay, and velocity has two components, that is direction and speed at which the parameter x moves. Now, The velocity, obviously, I don't want too much of history baggage with me all the time. I would like to, at some point of time, do away with my history baggage. So therefore, there was also this exponential moving average, a decay average of the negative gradient. That was to this factor here, this mu here. Okay, so this is a decay factor. That means that mu, in the first time you'll have mu times v, then it will become mu square for an older v, right? Mu cube. So the history is also fading out. Basically, that's what we want to do. Right? Okay, so this is again recap. This is important, so I'm just doing a little recap. And then we found that two alternatives possible. One is a momentum computed based on the previous iterate. So where are you going to compute the gradient? That's the question, right? Will you compute the gradient after the velocity update or before the velocity update? So here you see in the Nesterov case, there's a gradient after velocity. And in the left-hand side, the Polyak case, the gradient is at the previous iterate, or rather current iterate. So you have gradient current iterate, you have gradient after velocity at current iterate. Okay, that was a differentiation. Okay, so what did it yield? So we have this Polyak heavy ball momentum as the first option, which adds as inertia term. And as I said, you have the gradient at the current iterate, and then you add a velocity term. This velocity will of course have this exponential decay. Right, through this mu t. And it turns out that for smooth and strongly convex function, it's going pretty okay. For smooth and strongly convex function, gradient descent gave you kappa minus 1 by kappa the whole raised to t. And this gives you square root kappa minus 1 divided by square root kappa. As I told, this shouldn't be bothering us. Okay. So for all practical purposes, and by the way, this was also the tightest, right? This was the tightest. Comparable and commensurate with lower bound. Which we kind of alluded to in the last class. So this seems to be fine for smooth and strongly convex functions. We might have a slight challenge when it comes to just the smooth case, only the smooth case, without strong convexity. So when I say only smooth, that it's only smooth plus vanilla convexity. That goes without saying. Is that okay? Please interrupt me if you have questions. The whole purpose of hybrid class is that there can be more discussion. So this is our recap from last class. I kind of abruptly ended here, so I just wanted to spend a little bit more time. This clear? Somebody had a question towards the end of last class about this. Was it yours? So the question is, error bound we had was raised to 2t minus 1, right? All I'm saying is this squared you can take inside. These are all upper all factors between 0 and 1. Oh, sorry. Yeah, can you repeat what's your question? So my point is as follows. This entire number is going to be between 0 and 1. So let me again highlight this point. So this entire thing you're exponentiating is just between 0 and 1. Something. Okay. And you're getting some similar factor. So that doesn't matter. So like so you can, I mean, you square it, it will be again between 0 and 1. So then whenever you have something, some factor raised to 2t, you can just think of this as that factor square raised to t. 0. Hence we are not bothering so much. Okay. Okay, so this just to kind of contrast what's happening. Gradient descent is oscillating here, whereas heavy wall, or as we see with Nesterov, you have some course correction. Course correction is because of the velocity. Now it's not that it's like heading straight with star. It's still having a little bit of oscillation, but the oscillation is reduced. Okay, so this is reduced oscillation. So within 3 steps, you have moved much further away. Look at the amount of movement you've got overall. In comparison to just this. This is the movement you can. Okay, but let's now look at Nesterov and see can it help us in that smooth case. That's what our interest was, and I kind of just mentioned that the Polyak is not going to be great for smooth case. We haven't done analysis or presented analysis, but you can believe me that Nesterov turns out to be a better option, and we'll not be doing the proof in the class, but I'll be telling you what the basic idea is. Okay? Just recap that Nesterov does the updates, the gradient computation after velocity, right? So post velocity update, gradient computation. Okay, so what exactly will it look like? And this is going to get us to t plus 1 square. That's our target. So what will the update look like? Okay, so I'll tell you, it doesn't look that neat. In my convex optimization course, I spent a lot of time, but I don't want to do that here because I'll tell you how this gets used in practice. And interestingly, some of the advantages you get through Nesterov's accelerated gradient, you can also get some of the advantages through proper line search. Okay. So there are 2 reasons. I'll do some demo later on. But let me show how this fixes it, right? So the fix goal, I mean, at least in theory, this gap is fixed. But let's quickly see how that gap is fixed. So I must tell you, I find it a very, I mean, the exact update is very unintuitive. Right? In terms of exact step, the algorithm might be intuitive. So let me just clarify. They're basically unintuitive details. You want to be more precise. The details are somewhat unintuitive, and the proof procedure is certainly very complex.
What exactly do you mean by fixes this?
Fixes the gap. So recall that this in red was lower bound, right? And this in blue, what we had shown was obtained using gradient descent, the vanilla gradient descent. Is it okay? That's what you're fixing it.
So the you get from nested of will be lower bounded by the red part rather than
Yeah, epsilon, yeah. In the epsilon that we'll get lower bounded by something like this. I mean, t plus 1 square. Okay, so when we say fixes this, we will get something like 1 upon, I'll get something proportional to 1 upon t square. Omega, to be more precise. Okay, so I will refer you to these more detailed notes. And the thing is, in these notes, okay, I'll make a bunch of comments here. So in these notes, I don't present Nesterov only for gradient. I present this for something called generalized gradient descent. And even there, for generalized gradient descent, there's I present a couple of possible cases under which this holds. So proof is generic enough for. I'll talk about what is generalized gradient descent later. For example, if you have heard of proximal gradient descent, that's an example of generalized. Proximal is an instance, proximal gradient descent. Have any of you heard proximal? Keyword? Okay, so the proof is a lot more complex because also I've used it in more general settings. So here's the, yeah, here's where I prove it. So this is Mr. Accelerated Gradient Descent, and so it's a slightly involved proof. And because I said it's generalized, it has this prox operator, etc., etc. So we'll talk about proximal, of course. It runs into multiple pages. I don't think I'll do this in a machine learning class. Okay. So you can feel free to go over it if you want. But let's do the steps. What are the steps here? So the algorithm is as follows. So I'll tell you the intuitive parts and the non-intuitive parts, we'll keep them separate. Okay. So intuition is that we're going to have an xt. You can make notes of these if you want, and before we get lost in the relation. Right? So we're going to have xt as velocity. Okay, at based on t bit rate. t minus 138. Okay, so it will be something like, but before I write down the update, yt will basically correspond to update post gradient computation at xt. So at xt you do the gradient computation. So overall your updates will look like, yt plus 1 equals yt, sorry, xt minus gamma t gradient f of xt and you will set your xt plus 1 for the next iterate right away. So xt plus 1 will be this decaying average 1 minus mu t, that's a decaying average of yt plus 1. So basically mu t is the decaying average, so it's a convex combination of yt plus 1 and yt, but you can expand it if you want. So these are the basic updates. Okay, so this so you can rewrite this if you want. I think you can rewrite this as yt plus 1 plus this mu t. Okay, so times yt minus yt plus 1. Okay, I've just rearranged it. So I'm basically now computing my momentum for the next step in xt. Is it clear? So this is the velocity component, right? This is the velocity component, and I'm adding that velocity component with the decaying factor mu t to yt plus 1, and then in the next step the gradient will be computed at xt plus 1. This is the basic idea. So there will be two of these terms. One is gamma and the other is mu t. Okay, so the dirty part is how. Okay, there's actually one. There will be a couple more components, I think. This gamma is going to be obtained in terms of another factor. This gamma is a little dirty part, right? Or expression, update expression. For gamma t looks messy. That's the complex part. So gamma t itself will be obtained using some lambda. That lambda will be obtained, I think, in terms of previous lambda. So this basically the gamma is going to decay, but the gamma is going to decay according to some other factor lambda. So it's the update expression looks complex. It's a decaying expression. And I'll just add this qualifier, so decaying update. So the second is it decays. Okay. Huh? Yeah, not exactly exponential. Yeah. It's a slightly complex, yeah, in decay, not exponential. Okay, so and this mu t itself, so mu t is, so there are options. Okay, so mu t doesn't have one solution. There exist options for updating mu t. Yeah. So it'll be nice if you can write this down so that you don't get caught up in the details in the next slide. Can I move on? Okay, so now the slightly messy part. So lambda naught is what will determine how the gamma will decay. So I talked about, the update expression for gamma, it's complex and it will decay. So that's exactly what I'm showing you. It'll decay, but it's not that it decays from the word go. Initially, lambda naught is 0. In fact, I think in the code I have lambda naught I have set to 1. I think there are multiple options. So, but anyways, here lambda naught is 0, and in this particular instance, lambda t is 1 plus 1. Yeah, this is interesting expression, which involves this previous lambda, and this gamma is determined by the lambda. Okay, so we compute the lambda t plus 1 and then obtain the gamma. The gamma is always greater than or equal to 0. That is ensured. Okay. So what you do? Well, initially you have y1 and x1 the same. I mean, there's no momentum initially, right? So the way we are specifying that is no prior momentum. So therefore you begin with x1 equals y1, y1 is an arbitrary point, and then
Gamma t should be less than equal to 0.
Gamma t should be
Less than equal to 0 because lambda t is always greater than equal to 1.
Lambda t, why?
So if you look at the expression, then 1 plus 4 lambda square t minus 1 is greater than equal to 1. So 1 plus that is greater than equal to 2. So divided by 2 is greater than equal to 1. So lambda t is greater than equal to 1. So 1 minus lambda t over lambda.
I did make a mistake. So this mistake here. Gamma not be negative. Okay, so let me check this.
It could be lambda t minus 1 and minus lambda t.
Lambda t minus 1, yeah. Let me actually look at my code, what I've written. That could be the case. As I said, that is a slightly unpleasant part. This could be lambda t minus 1. Let me check the code. Sorry? Yeah. We'll just check this. Okay. Yeah, and then as I said, yt plus 1 is obtained as a gradient descent update step on the xt. Right? The xt is used in both places. So note that we are deriving our momentum with respect to xt. Sorry, a gradient descent. Gradient descent on velocity update. That's basically the idea of yt plus 1. And then the next step unfolds, which is how do I now memorize the velocity for the next step. So this is the velocity for the next iterate. Or velocity update. It's not just velocity. Use velocity update for next iterate. And you could think of, as I said, the velocity would be, this would be the velocity. We highlighted here. Okay, so you could think of this differently. You could say this is xt plus 1 is yt plus 1 plus mu t times yt minus yt. Okay, now mu t is again said to be diminishing. Okay, that's another thing I forgot to point this out. But mu t is also diminishing. Like okay. Anything else here? Otherwise, I'll probably like to do Japanese. Okay, any issues? Sorry? So why couldn't we have a nice expression for gamma, right?
Yeah.
So I'll talk a little bit about line search methods today, and you'll find that lots of these line search methods are inspired by some kind of interpolation. See, you want these step sizes to diminish. That's obvious, right? We'll see more so in case of stochastic update. Stochastic gradient descent, the step size diminishing is even more required. Now, how should it diminish? So, one possibility is keep halving it. Right? But there are more complex approaches where you try and interpolate. The interpolation is based on something called a sufficient degrees condition. Okay? So maybe I'll make a note of this here. May not be able to elaborate. So this is inspired by sufficient two things. Okay, so let me make one is sufficient. Actually, let me just type it as easy. Make a note of this. Inspired by so sufficient degrees condition. If you remember, when we did Lipschitz smoothness, we actually found a sufficient degrees, right? But it's not always the case. Actually, we'll have Lipschitz smoothness. So there are some Armio conditions, which, as I said, I'll talk about today. The J side. The Armio conditions is Goldstein conditions and so on. I have put some extra optional slides prior to mid-sem, right? I talked about those conditions. Again, it's optional. So that's one thing that is inspired. And the second is to have this condition satisfied across epochs, across iterations. You may do some interpolation. Okay, interpolation on gamma, the step size across iterations to help satisfy these conditions quickly. So these are the two major motivations. So this linear, why we see such complex expressions is because of this kind of interpolation. Not necessarily linear, they could be polynomial interpolations. Is that okay? A good question. Okay, with that, I want to move to the demo. So this was proved basically by Nesterov that if F is convex and Lipschitz smooth, not necessarily strongly convex. Okay, again I am pointing out. Not necessarily strongly convex. So under these two conditions, the f by t minus f x star is less than equal to 2 LR square divided by t square. So if you want an epsilon greater than some value, what do you do? So if the difference should be less than equal to epsilon, what do you do? A sufficient condition is
epsilon less than 2 LR square.
yeah. So epsilon should be greater than equal to. You just put it here, right? So this is what we do. And then that would be t square omega 1 upon epsilon or t omega 1 upon epsilon square. Sorry, square root epsilon. 1 upon square root epsilon. I want to put this out of context here. Okay, so now let's see. This is great. Isn't this the lower bound? Lower bound will have this t plus 1 square, right? So I had this omega. Oh. Yeah. Okay, so again, the proof is there also in these notes. I don't think, I mean, I've followed a very different convention, notation convention than Mr. Rao. What is wrong with my page? Follow this if you want the detail. Now, I think with this, yeah, so this matches the lower bound of the constant factors. Okay, but for us now the exciting thing is how does it affect in practice? Okay. So let me just paste the link to this here as well. Okay, so I'm going to run through this a little carefully. Let me. I provided this notebook long back, but we never actually stepped through it. So this is the SMS spam labeling dataset. This is going to be a canonical dataset on which I illustrate many algorithms. So we have used the logistic loss. Is logistic loss strongly convex? No, right? Well, if you add a regularizer, you get it. Let's say for the time being, we stay without the strongly regularizer. Okay, so first thing is we'll do simple gradient descent with fixed step size. This is visible to everyone? Beginner, right? And we have a fixed step size. We can try with different learning rates, okay? But I will use some fixed step size. And what I'm going to compute is the function evaluations. The number of times gradient and function computation are done. The optimality condition we're going to use is the max component of the gradient vector. So take the gradient vector, right? And you want the max component of the gradient vector to be very small. Basically, you want the gradient to go to 0, which means you want every component to go to 0. But if the max component is significantly diverging, you're probably not close enough to 0. So instead of looking at a norm, which can be a bit deceptive, L2 norm can be deceptive. The L2 norm might only look at sum of squares. And now sum of squares, it can diminish, right? The squares can just make a value unnaturally look unnaturally small. And it doesn't look at the smallest value, sorry, the largest value. It looks at all values. So therefore, infinity norm is often used convergence criteria. Okay, so this is the default gradient descent. So our function objective, what we're going to pass is the logistic loss. So it's declared above. And we keep iterating, keep printing the function evaluation. The alpha, which is obviously going to be fixed in this case, and the function value. Right? and you're going to update your W as W minus alpha G. Very simple. Until either the the largest component of that gradient becomes less than 0.01 or some maximum number of evaluations is exceeded. So here we have, when we call, we are setting maximum evaluations to 250. The lambda value we are passing as 1. Lambda, okay, that's a regularizer because we add a regularizer to make it strongly convex. Though we are not really using strong convexity. Okay, so let's look at it. Function, it goes until some 250 evaluations, basically all the evaluations. And look at the function value 2713.28. Trying to minimize it. And the optimality condition is 14.43. Not a very good thing to have. Okay, so this is Nestor accelerated gradient descent implemented here. So just made some notes here that the lambda in the slides is t. Lambda t minus 1 in the slides is t, and lambda t in the slides is tp. We could write lambda here. But that's the smaller issue. The more important thing is I have not used exactly what I have in the slides. You are welcome to try what is mentioned in the slides and shared with you. Here we have used ideas of Armio condition because I'll be talking about some Armio conditions now, and based on that line, basically the line search. So I've used alpha based on that line search. And there are multiple versions, so there are 4 versions in the same notebook. This is the second version I evoke. But otherwise, all the other steps are basically, and you find out that this is not very different. This condition is not very different from what this complex thing we have done to find gamma. Okay. So it's pretty much the same. And now, okay, by the way, there's something called backtracking. What I didn't talk about is backtracking. So moment you do line search, you're basically searching. So let me, so I'm going to refer to this here. So the idea behind line search is that if I'm at this point here, and I want to know how much to move in the direction of the gradient. Should I move this much? Should I move this much? Should I move this much? Okay, I mean, I'd rather let me show the form of level curves. That's easier. Okay. So yeah, should I be? If I'm here, should I be moving all the way here? Should I move this much? Now, what backtracking does, it says, okay, I'll let me try move this much, and then I'll not do the update. I'll check for some condition, which I said is a sufficient decrease condition. I mean, I gave a hint of what sufficient decrease means with Lipschitz smoothness, right? But you can compute conditions without computing the next iteration. So the idea in line search is also called ray search. Well, it's called line or ray because lambda is always, or the step size alpha is greater than equal to 0, right? Therefore, it's called ray. But most often it's called line also. So don't get confused. Line ray search. It will take a step or consider, not will really take, will consider some step size. Okay, alpha. And then it will check if some decrease condition is met. The Armio condition is met. I'm going to use a different color here. So we'll then next check. if some sufficient decrease condition is met. Okay. So it's basically now going to probe into this point here. I'll now have to move back to the function space. So we'll have to do that because with level curve space you can't get an idea what function sufficient. So what here is here. You just flash this. So let's look at this. This is from the Moodle. I had posted these, right? The easiest to just show this. Okay, here. So basically, it's going to check. You can see this. Is this visible? I think I kind of gone very fast over these in the previous itself. Basically, there should be sufficient degrees. If you are here, it should be that I move so much that I've actually started increasing at the other side. You see this side, it started increasing. Let me just take a clip of this. This is easy. Okay. I didn't take a clip. Doesn't take a clip, anyways. So I'll have to present here itself. So this is what we are concerned about. We don't want to take such a big step that we have exceeded the or we are tending to the value from where we began, right? So that's exactly what RMU conditions look at. I'll put that clip later on. Okay, so you check if some sufficient decrease condition is met, and then with respect to this, if not, then what do you do? I'm here. I have kind of overstepped. If not, I will shrink the value of lambda again, or the alpha again, right? So if not, shrink the alpha. Is this clear? That's the basic idea. And you find that, in some sense, accelerated gradient descent is doing that, but it's not just doing that, it's also looking at direction. See, this problem is line search is only looking at the scalar. Accelerated gradient descent goes beyond the scalar to also the direction. That's the additional part it gets. So, I mean, just to kind of point out, right? So this is shrinking, it's doing lambda, all of this is doing. But beyond the spirit of line search, it's also getting momentum direction. Okay, so let me go back to the plot here. So to accelerated gradient descent, that's what we have done here.
Line search tries to find the maximum alpha such that we are still decreasing.
Yeah, exactly. So line search tries to find the summary work. Okay, is that line search is trying to find the kind of maximum alpha so that there is sufficient decrease. But here we are doing line search and also, as I said, the momentum direction. Okay, now just contrast. Let's just contrast. We got some 14.43 condition, right? And function value 2713 after 250 iterations. But let's look at what accelerated has done. I mean, it's got us much closer, right? You see, this is quite impressive. Any people on the call, in case questions, let me know. So this is interesting. Now there's a backtracking here happening here, as I said. We are counting backtrackings. Backtrackings is because you might have overshot alpha. Okay. So yeah, this is to convince you that accelerated gradient descent has worked, right? But I have couple more use cases here where you look at this line search itself. So gradient descent with RNeo backtracking line search version 1. So I have kind of also written in LaTeX what these do. So simple line search strategy, start with the large value of alpha. This is the simplest, okay? Divide alpha by half if it doesn't satisfy the sufficient degrees. The sufficient degrees is f w minus alpha g. G is a gradient. W is the current parameters. Should be, so this is sufficient degrees. This should be less than equal to fw minus gamma alpha norm g square. You can see it's kind of inspired by strong convexity. It should be, there should be that gamma g square gap. Rather inspired by the sufficient degrees condition we get with Lipschitz smoothness. So you'll keep decreasing alpha. That's the simplest line search strategy. Okay, this is version 1. Let's see what happens. So you can see version 1. I mean, it's better than gradient descent, right? Look at gradient descent after 250 iterations, the condition value was pretty high. I mean, in 250 it's done well. It's not got as far as accelerated, which is okay, but it's impressive. Is it okay? But let's look at version 2. The issue is that alpha may quickly become very small because you have initialized alpha once in the beginning and then keep on dividing by half. I mean, then alpha just can become 0 or very close to 0 because of numerical precision errors. Actually, gamma is there in both. No, gamma is there in previous. So the same condition is used there also. So gamma is some kind of scale factor. If you remember, I had shown this plot here, right? So there's this beta here. So I mean, I've used beta here, gamma and the code. So you have to be a little robust on notation. The different notations are used in my different slides. It's very difficult to stick to one notation. I'll tell you, just impossible. So you should just become robust, become thick-skinned in terms of notation. This beta is our gamma. This T is our alpha. Okay. So now what we are doing is, instead of just setting, keeping on dividing alpha, the first line search strategy, the second line search strategy, I'll say I will reset alpha. After every step, I find a sufficient degree, I'll reset alpha. Makes sense, right? Yeah, let's say the same large value. So this reset alpha to the same large value. Now you have a problem. Now you have identified one issue because all the advantage I got from my search in the previous iteration is all lost. So I have a lot more backtracking here. See, that's why in this code we are counting backtracking steps as well. Okay, what we print here is function value alpha, and then in the end we count backtracking. Okay, so now with 34 epoch or 34 function evaluations, it's done well. It's gone down. It didn't require 250, right? It did not even, it exited. But it has a lot of backtrackings, 23 backtrackings. If you look at the previous one, I think the backtrackings I had printed there also. 7, only 7. It's obvious. The previous one, the version 1, kept backtracking and used that backtracking information in the next iterate. This guy is going to start from scratch, so it's going to backtrack a lot more. No surprise. Is this clear? So now this is our version 2. Yeah, I mean, this is best done through, you should run it. My request is run it, if the collab is not provided.
But this does look like kind of overfitting, like in this number of steps you had
Which one? This might overfit, yeah. Yeah, but then you design your objective function with regularizer, right? So I agree. I mean, there are always pros and cons. But at least given the objective function is doing a fair job. Okay, so now let's look at version 3, which says, okay, why should I, this is exactly the idea, why should I backtrack so much? That's where interpolation comes. I don't want to start from the same large alpha every time. I don't want alpha to keep on shrinking. I'll interpolate the alpha. Okay, that's where you saw that magic coming even in the accelerated gradient descent. Yeah, please ask questions. Today I really want this to be interactive. Let's be completely grounded. So here's the alpha. Some polynomial interpolation. How I this exact form will not get into. Okay. But what we are doing is basically looking at the current function evaluation with respect to the function evaluation before starting the backtracking. Before you did any backtracking, what was f? What is current? So I'm kind of doing some polynomial interpolation. Get my alpha. Minimizing passing through fw, the derivative of w and fw minus alpha g. This is okay. By this way, f dash w is basically think of it as a function of alpha. Okay. With version 3, you would certainly expect number of back. Oh, no, what has happened? This should have helped improved, right? But what has happened? Backtracking has increased to 127. Function evaluation is also high. Why didn't it work? Okay, so idea is that initializing alpha equals 1 is too large in practice. So what you initialize alpha is also important. Okay, so the interpolation has exposed potential issue with what alpha you initialize with. Because interpolation will be as good as what you're interpolating, right? So this version 4, which seems to be a good idea, just some use a heuristic. It basically uses alpha as 1 upon norm g, the gradient. Think of this as there's 1 upon the Lipschitz continuity factor b. But you don't have access to b, so you are using norm g. So you're basically now you're kind of clipping alpha, min of 1 comma 2 blah blah blah. So again, a lot of it is tried empirically and based on empirical knowledge, and that's why I'm not running slides through all of this. It's just best to try it. Okay, so version 4, I would say a fixed version of version 3. Yes, this is very impressive. Backtracking is reduced, number of evaluations is reduced, 17. That's it. I mean, if you compare this against accelerated, you'll find, well, accelerated, what is it doing? This seems to be good enough, right? And I mean, this is not a synthetic data set. This is actually spam data set, text data set. It's not totally cooked up. So accelerated has value. I'm not saying it doesn't have value, but the story is accelerated is doing the additional direction evaluation, which might be helpful in many, I would say, many stochastic settings. So stochastic settings will again revisit accelerated. Okay, so just let's quickly look at these different line search techniques. I've hidden accelerated. I don't want to embarrass accelerated here. So accelerated might look worse than V4, but it certainly is better than the others. That is better than V1. Anyway, so, but you see V4 is pretty good. Right? With just this one, is it visible? This one, V4, this has dropped very quickly. I mean, V3 was a slight aberration because of, it's just alpha equals 1. What is the interpolated value is important. So V3 was kind of a precursor to V4. So we can ignore V3. The V2, which is green, was certainly an improvement over V1, which is in orange. The fixed alpha was slightly better than orange in some cases because it's not doing backtracking. See, backtracking also takes some time. Okay, so number of iterations, you kind of you'll find that yeah, the V4 really does well. And what we have done in the next plot is say, okay, the behavior initially is fine, but what about subsequent behavior? So 50 iteration 50 onwards, we have looked at the plot here, and yeah, V4 has done a great job already. V4 is out, huh? Yeah, V4 is out of this. It's already done basically. Yeah, so it's not there. But you can see V3, V2, and eventually even V3 is doing better. V3 is so an idea. So now basically as our default line search condition. If you use that, then you will find okay, just 5, which is very good. Any questions? Go back to this. So I'd like you to summarize your learnings. Maybe I can type out as you speak. Whatever you learned. Anyone on the call here? Yes. Learning, summary, whatever. I mean, what do you understand from this entire discussion? Key points, takeaways. Initialization of alpha matters. Right? I would say not only RMU condition before, but even accelerated gradient descent does that well, because it's combining the direction with the step size. Okay. Any other learning? Yes, please. Anyone on the call? I don't know if you're speaking or I can't hear you. So re-initializing alpha matters. Actually, in the alpha in the collab notebook, which is gamma in our.
Why did resetting alpha give better results?
Resetting alpha gave better results because, well, it gave better results in one sense. It increased number of backtrackings, but it gave better results because the alphas are not just, if across iterations or you're just making alpha 0, then the steps are trivial, right? There's hardly any step that you're taking, right? So it becomes too small and the steps will become meaningless, right? Anything else? Any other learning?
What value we are resetting alpha that relates to the original alpha.
What value one resets the these alpha step size matters. Uh, especially when one is doing linear interpolation, polynomial interpolation. Great. Good. This is very nice. Any last point? Anything? Any good thing good to say about accelerated gradient descent? Anyone on the call? Anything you like about accelerated gradient descent?
You can both controlling the direction as well as the step size.
So you're controlling both direction and step size. There seems to be something more principled about the way you're controlling those two, right? It's leading to better convergence. So it's reducing that gap. So
I did the line for condition 4 converge faster than
why did the line search condition 4 converge faster than accelerated? Because I think accelerated also you can use the condition 4. I didn't use. You can. As I said, okay, the question coming from the class is, can we use the RVO conditions in accelerated? Yes. In fact, as I said, let me go back. Very good question you have asked. I think I have mentioned this upfront. Our accelerated gradient descent was inspired by our implementation was the version 2. I've said that. Has the Nestor accelerated gradient descent implementation below has also incorporated RVO condition V2, not V4. You could incorporate V4. So again, as I said, I think the V2 gels very well or aligns very well with the default version of accelerated Nestor of gradient descent for which the proof is there. I mean, it's not that there have been proofs for all versions. You can have all permutation combinations. So you could, in fact, you could do that. It's a good point. Pardon? For both gamma and mu. Well, mu is, as I said, mu is coming a little exclusive to accelerated gradient. Mu is that the decay factor associated velocity, right? That you don't have, and that doesn't exist even in line search, right? So you can do it only for gamma. That's effectively what's being done. Okay. So seems to be a principled approach to determine the direction using velocity as well as the step size. However, we could improve our implementation of Nestor accelerated gradient descent, right? And improve it in the sense, improve it beyond the current RMU condition V4, sorry, V2, the kind of default. To say is V4. Okay, but again, I want to make a note here that this is, you can use V4 for gamma T. Right, mu T, for mu T, the updates are exclusively for accelerated gradient descent. I mean, you don't have an equivalent of mu T for line search. Okay, is this clear? Any other point or we are done? Unless someone else has more to add, we'll probably move on. Anyone on the call? Okay. So summary of results so far as analysis is concerned. Um, yeah, this is so far through acceleration square epsilon, right? And as I said, matching the lower bound. The omega. We are 1 upon and this for smooth functions without convex, strong convexity. Of course, if you have smooth and strong convexity, then you probably, and that's one reason why accelerated might have not made a big difference for the logistic regression plus regularizer. Right? There you have got both strong, smooth and strong convexity. So this could be reason why Arnio V4 from this, right? He just said, okay, come up with a better step size. You don't need acceleration because you already have smooth and strong convexity. So it didn't necessarily benefit so much from the all the hard work we did for smooth functions without strong convexity. In multiple ways you could explain. Okay, now let's look at the next chapter, the next part. What if you can't compute gradient at all everywhere? So we know that the subgradient descent to a rescue. It's like gradient descent, but you're replacing um, the gradient with a subgradient. But when we say replacing gradient with subgradient, there are so many subgradients possible. So therefore, we have a notion of any subgradient. So you just take any subgradient. Remember, right? We even as simple as L2 loss, where we discuss the ISTA algorithm, something like this. You have an entire cone. So you can pick any of these at this point of non-differentiability. So because now you have any subgradient, you can possibly consider multiple subgradients. You can try descending along one, right? You could say, let me explore, let me try this direction, let me try this as a subgradient. So this might be, I mean, even at a particular iterate, right? This could be h t minus 1. But there could be another one, which could be this in blue. And we may want to call it h2t minus 1. So you can have multiple possible directions for the subgradient case, right? I mean, for logistic regression, it doesn't matter. But for hinge loss, you made some problem, right? Hinge loss, this will matter. Okay, so therefore, a lot of the analysis you will find is not with respect to any, but with best. In fact, there's a small caveat. Calling it descent itself is a little misnomer. Will it descend at all? I don't know. Gradient descent, well, there's some assurance. But with these, you can't even say this descent is guaranteed. Well, gradient descent also, if you don't use the right step size, it will not descend at all. But things are a lot more iffy with subgradient descent, and even more iffy when you start looking at stochastic approaches, which will be the next thing. So now we are going into murkier territories. So this is this is really murkier than gradient descent, but less murkier then stochastic gradient descent. So then that's the rationale behind having this f best. We'll not take one, but we'll take the best there, xt best, and we'll basically keep track of the best xt among xt1, x1 to xt. So to update each xt, there are basically two ways. Okay, so fixed step size or diminishing step size. Fixed step size for all values, like our 9 gradient descent, but I'll tell you this doesn't work well at all. Or diminishing step size is what you typically encourage, where you're saying that the gamma t's go to 0, but the gamma t's also should go to 0 in some particular way. Now, it's possible that gamma t's go to 0, but yet their sum is infinity. That's possible. But then we'll see that there are other conditions. So what about, let's say t equals 1 to infinity of gamma t square? Is it a good idea that this becomes finite? Does that help? So these are questions you have. Okay, so the two things we'll have to take care. Again, I'm going to highlight here. The first care you'll have to take here is this. Okay, so this one in pink. The additional care 1. And the second care you have to take is the one in orange here. Is what the step size should be, starting mattering even more. I mean, today's class was to kind of eye-opener on how important the step size is already from army of conditions. But you'll see that even more pronounced with these murkier approaches. Right? So this is additional care 2.
So the point of non-differentiability, how will we get which is the best for x?
Which is the best one? No, function value wise. I mean, you have all these. So it's a good question. So if I have, let's say there's a non-differentiable function, or non-differentiable everywhere. Okay, so let's say the function was like this. So it decreased and then increased. Basically, it's increased in the sense from here. Okay, let's put it as point, right? This point, from this point I went to this point, and then I went to this point. It's non-convex, but even in the convex case, it can happen. So this is 1, this is 2. Let's say this is 3. I'm oscillating a bit more. 4. I'll pick the best of these, and maybe 5 again goes up for some reason. So this is 5. So the best in this case is going to be this guy. F or rather xt, right? X5 best. Up to 5 iterations, the X5 best is what? X3. Is this clear?
So why did you include summation gamma t into the
Summation gamma t being
why should the sum be
why should the sum be infinite? So we are saying that we don't want to put too much restriction on how fast they're diminishing. They should go, but so let's take an example, right? So what about, let's take an example. Gamma. Okay, let me just complete this. I think I should move this x3 a little down so that it looks clearly below x4. Okay, let's look at your question. The question was, why do we need or why do we need to cater to the sum of gamma t being infinity. So let's take the example of gamma t is 1 upon t as against gamma t is 1 upon square root t. What do you observe with each of these? Both the sums go to infinity? Both go to, no. Is it a bad step size? I mean, it doesn't look like a bad step, right? It's diminishing. In fact, in some, just backing upon some of our previous experiences, I think we have seen some versions of these. Okay, so these are commonplace, and that's why we are saying let's not be impractical about the steps. Upon these summation of it doesn't go to infinity, right? Yes. So 1 upon we'll see. So what happens? That's bringing to the next question. What if you make it finite? Does it help? So I don't want to jump to the conclusion. Let's investigate a little bit more. But good questions. Okay, so here is a convergence analysis. So if you have f being Lipschitz continuous with constant L, so we can't talk about smoothness, by the way, right? Because we are now looking at subgradient. So subgradient would mean smoothness or strong convexity ruled out. I mean, at least everywhere. You can say at some places they may be. In general, you can rule them out. So therefore, we are now putting up with Lipschitz continuity, the constant L. And if you assume that your points are within some radius R, that's again something we have been doing since a very long time. Nothing new. So this is x star, and let's say this is the x1. We have just 2 minutes left here. So under this, if you have a fixed step size, option 1, the x best, fx best, as t goes to infinity is less than equal to fx star plus L square t by 2. Not very happy, right, to see this. I mean, it's just like as t increases, then the gap is not anywhere diminishing, right? So basically, you're saying that okay, it's less than equal to f of x star, but then L square t by 2 is there. Yeah. So, but if you, so the diminishing step size is important. But if you have diminishing step size, let's say order 1 upon square root t, which which has a summation going to infinity, then you'll basically have this xt best is less than equal to f of x star plus order 1 by x square root t terms. So we'll do the proof. I'll be posting the proof. It's a
both are finite when t goes to infinite, so it will be anyway less than that.
No, but this is at least somewhat helpful, right?
No, I am
Huh.
t goes to infinity, so
Well, all you're saying is it's not terrible. I mean, yeah, there's not much happening here. This is our only interesting case. Okay, so 1 upon square root t, not something to be excited about, but this is what this is what subgradient does. I'm going to leave this as homework. Please, I mean, I don't want to spend again time doing proofs in class. Please do have a look at it. And it's a simple inequality with telescopic summing. What happens? Okay, so you'll find this expression gamma square L square. So that possibly will open up the doors of something to do with gamma square. So, so if you, this is the part we want to draw our attention to. So I will spend some time on this part, but please do go through the proof so that we quickly converge on the take home from here. Okay. So yeah, this is the convergence analysis which I will kind of. So until this point, I would like you to just read up. And basically, you'll see subgradient method as convergence into omega 1 upon square root. And then we'll move on to stochastic. So this is an important homework for you. Any questions? Sorry? Slide number 30. Yeah. I'll be posting it. Any questions? 1 minute past. So was this helpful? The pace is okay? The pace of the class? Thanks. Thanks for joining me.